Good morning all. Shall we charge this supercapacitor bank? Three 2.5 volt supercapacitors in series, 7.5 volts. Here's a little power supply set to 7.55 just to offset a bit of voltage drop in the cables. Switch on and the supercapacitors charge up. It's so exciting. I love doing this kind of thing. However, that's not really what this video is about. Now, this video is about this thing, but it does have some connection with this supercapacitor bank, so we'll come back to that. But let's take a look at this little module. It's an inverter. So this is a commonly available module on eBay. I bought this quite a while ago. I think it's an inverter for CCFLs, cold cathode fluorescent lamps. It's billed as a 12 volts in, that's on the primary side here, to 220 volts out, AC, but there's also this bridge rectifier on here, this little component here, which turns it back into DC. So I've got the red and black crock clips on the DC output after the bridge rectifier, but the AC output is on these two, so that I can take a look at that as well. But what I'm particularly interested in is not the 12 to 220 volt inversion. I'm interested in how lower voltage you can put on the input side of this and actually get something out of the output. So let's take a look at that. The connections on this thing are a little bit higgledy-piggledy. So what I've done is I've just routed the negative output from the bridge rectifier over here, so that I've got that on this side of the unit, and I've got pos and neg input on this side. So I'm just going to connect this up to my power supply. It's probably going to have to sit upside down because that's where the connections line up. So I've hooked up the output of the bridge rectifier, which is after the transformer, which of course is after the oscillator, so that we can look at the DC voltage. Now I'm using this Mustool graphical multimeter today just for the amusement, because I kind of thought it might help us see the AC output from this thing. So let's switch that on to DC volts. That's showing 0. That's good. Let's get my solar power supply. It's going to have to come in here somehow. Plug that in. And, well, we might as well shovel 7.55 volts into it, since that's what it's set to. Let's see what we get out. And, yeah, we're getting 212 volts DC. Right, so what I've done now is I've hooked up these two green wires to the AC output. So that's on the AC inputs of the bridge rectifier just before it's converted into DC. I'll just leave these plugs here. I'm going to switch this to AC volts. That's Hertz. And we'll just see what sort of AC voltage we get with 7.55 volts going in. And it's lower, it's 140.4, but then that's probably RMS volts, so that kind of figures. Now, since this is supposed to be 12 volts in to 220 out, let's see if we can get 220 out. Let's switch back to volts and start winding them up. So at 9 volts we're getting 160 out, 10 volts 175 out, 11.5 volts 192 volts AC out, and at 12 volts we're getting, well, just about 200 volts AC out of this little inverter unit. Now I wanted to use the graphing thing on here to see the waveform, but I'm having some trouble with it. It's not really showing it very well, and it displays it as overload kilohertz, and that's because this thing oscillates at quite a high frequency. We've got the AC voltage displayed here, 200.3 volts AC, and we're getting some sort of waveform, but I don't think this goes up to very high frequencies. It says it's got a sampling rate of 200 kilohertz, so it should be able to show, I don't know, 20 kilohertz at least, or something like that. Interestingly, if you switch this to hertz, it's perfectly capable of displaying the frequency, and it is no hertz at the moment. What's up with that? I'm having a few issues with this Must Tool DMM, so I've dropped the input voltage to 5 volts, and now I'm getting 100 volts AC on the AC voltage range, but in the graphical mode it's unable to display the frequency. It's still showing that 104 volts, so we don't quite know what that frequency is. So let's now switch it to the hertz range, and yes, it is able to display that, and it's around 32 kilohertz, so it's quite a high frequency that this thing oscillates at off load. So switching now back to volts AC, I want to do the bit that I'm really interested in, which is how low a voltage can you put on the input of this thing and still get something out, and what in fact do you get out. So let's start taking this down. 4 volts, and we're getting 88 volts AC out. 3 volts, 65 volts AC out. 2 volts, and we're still getting 40 volts out of the inverter, 40 volts AC. Let's go down to 1.25 volts, 27 volts out. Now, can it work at 0.6 volts? Yes, it does. 12.6 volts out. How low can we go? Can we go to 0.5 volts? Just 10 volts out, and it's showing signs of falling away. 0.48, 0.47, 0.46, 0.45, still getting 5 volts out. 0.44, and that's collapsed down to nothing. So you can't run this below 0.45 volts, which is not surprising because there's a couple of bipolar transistors on there, and they're going to need this sort of voltage to get a current to flow through through initially base emitter to provide a collector current. But now if I start putting this back up, the up switch is very dodgy on this thing. That fires back up immediately, so there's no hysteresis. You just need that voltage and away this inverter goes. So at half a volt, it's doing 10 volts out. Now, remember the supercapacitors we saw at the beginning? That's the sort of voltage I'm interested in, so I want to take this up to about 2.5 volts because that's what those are. That appears to have changed range. So at 2.5 volts in, we're getting 50 volts AC out. And in case you're interested, these two probes here are going to my Tech 4 multimeter. That's DC, of course, after the bridge rectifier, and that's 64 volts coming out. So the point is, this little inverter module, which has a Royer oscillator, it's a very simple 2-transistor and transformer-based oscillator, Royer configuration. In fact, because this one's got a capacitor across the inductor, it's a resonant Royer. It's able to run with a very, very low input voltage down to half a volt. That gave us 10 volts AC out. With 2.5 volts going in, we are getting 50 volts AC out. So it's about a 20-to-1 step-up ratio from DC input to AC output. So for more information on the Royer oscillator, we go to Wikipedia, of course. A Royer oscillator is an electronic relaxation oscillator that employs a saturable core transformer. The classic Royer circuit outputs square waves, a modified version essentially by adding a capacitor, and that capacitor is on this unit, turns it into a harmonic oscillator or a resonant oscillator, outputting sine waves. Both versions are widely used mainly as power inverters. So here's the Royer oscillator circuit. We've got 2 transistors here on opposite sides of the primary winding. Power comes into the center of the transformer primary. Now there's a feedback winding which drives the bases of these two transistors and sets the thing into oscillation. And as we saw, this can run at incredibly low input voltages, really just enough to get current to start flowing through the base emitter junction. Now this one shows NPN transistors. Actually, this little module uses PNP transistors. This is a 2SA 2099, I think it is. So moving on in the article to the sine wave variant, the resonant Royer, you can see here that we've got a capacitor across the transformer primary. Now they also show in here a choke, and that choke is actually on the circuit of this little module, so I'll show you that in a moment. So that's in place. These two transistors are shown as NPNs down with emitters down to ground. On the module there, they're actually PNPs with their emitters up to VCC, and ground is actually the center tap of the transformer. There's a slight difference on that module there. These two resistors connected to the two bases don't go to the after choke point, they actually go to the before choke point, directly to, well, it's ground on that module. Now, as you can see from this circuit, the output is a sine wave, but on this module, this Royer oscillator inverter module, there's a bridge rectifier. So we've got this configuration where the secondary of the transformer comes out, goes through a diode bridge, and so we've got a plus one side and a minus the other to rectify it into DC. Now I'm sure if I dug out my oscilloscope we could connect it up to the AC output and see lovely sine waves and all that sort of thing, but in fact I don't really want to do that at the moment. What I'm interested in is using this for something entirely different. So let's disconnect it from this PSU, and I'm going to go back to connecting this to my supercapacitors and charging them up. So yeah, this needs a charge. This is down to 4.1 volts. Of course, this little voltmeter is drawing a small current from these, so they're dropping all the time. So let's put a couple of these little wire links in here, tighten that up and connect up my crop clips. I'm going to set this thing back to, now it was 7.55 volts, wasn't it, just to offset the little volt drop on the cable. So I'll set all that up and then we'll get charging. So I'll connect the positive. Now I'm putting the capacitor bank directly across the output of this power supply, but it doesn't seem to mind, but I've just got to be a little bit careful I don't short stuff out and have a big bang. So that's fine, 4.1 on the capacitors. I think I might have had a slightly dodgy connection on these crop clips. Switch this thing on. There it goes. And we're charging up. Now I've got to wait for these capacitors to get to about 7.5 volts before their protection circuits kick in and these little red lights come on. But while that's charging, I'm just going to place my little Royer oscillator inverter here, and I'm going to put the DC output across the supercapacitor. So there's the negative. Now you can see why I put these connections where I did, because it's all lined up with my pos and neg on the supercap. Let's put pos on, that should be fine, because the bridge rectifier here will act as anti-backfeed diodes, two of them in effect. I'll have a look at that in a moment, but let's plug this on and get these wires out of the way. So now I've got the output of my inverter connected up to the capacitor bank. Yes, on the bridge rectifier we've got the diode, of course, will point to the positive output. This one will as well. And these diodes, of course, have their anodes pointing to the negative output. So no DC current can flow back through the rectifier. It acts as a big blocking diode. Which also means, of course, that it's perfectly safe to short the input of the Royer oscillator, because nothing can come back from the capacitors back through this. It's also transformer coupled, so there's really no galvanic connection between the output of this thing and the input. Well, there is no galvanic connection. So still waiting for the capacitors to come up to 7.5 volts. and waiting for the little lights to come on. And shall we have a little wager on which one will come on first? Maybe. It is a gloriously sunny day today, and we're going to have a bit of a mini heat wave apparently. And the sun hasn't come round onto my desk yet, but I'm just going to lower the blinds so that we can see these three indicator LEDs, which are on the protection circuits of the supercapacitors. So they'll start coming on when we get near to 7.5 volts. So while this charges up, let me explain exactly what I'm doing with this thing. We know that this thing will invert, will oscillate with as little as half a volt on the input. So it's going to be fine with 2.5 volts on the input. We know that with 2.5 volts on the input, we're going to get something like 50 volts AC out. Now, of course, this thing cannot go to 50 volts now because it's clamped by the voltage of the entire supercapacitor pack, which is 7.5 volts. So the output is going to be held down to 7.5 volts. But it does mean that if I put 2.5 volts in here, I will be able to transfer energy from the input side through the transformer to the output side. It's rectified by the bridge rectifier, and then energy will be pushed into the supercapacitor bank. So what I'm planning to do is transfer energy from one supercapacitor to all of the supercapacitors. And because of the galvanic isolation provided by the transformer, I can connect these two wires to any one of the three supercapacitors, thus drawing energy out of that supercapacitor and passing it to the entire pack. So I'm going to use this as a supercapacitor balancing circuit. So we're at 6 volts. I'm just going to switch over to current actually. I'm doing this at 750 milliamps so that I can bring these up moderately quickly. Let's actually connect this to one of the supercapacitors. Now I don't know whether you can hear that, but there's a little whine. And the frequency of that is in the audible range. So I now think it's time to connect this back up to that DVM with the sort of mini scope function and try and see what that frequency is. Okay, a bit of reflection on here, but I hope you can see both the AC voltage and the frequency. Let's plug on the inverter to the center capacitor. And you can see that we've got 9 volts AC. Of course, we've got 6.5 volts DC. And the frequency is just 3.15 kilohertz. Now, off load, this thing was oscillating at 30 kilohertz. So the frequency has dropped massively. That's also not a sine wave. But in fact, what that is a clipped sine wave, because the oscillator will try to produce a sine wave, but of course as soon as the output voltage across the output of the bridge rectifier gets to this voltage, 6.6 volts, it's going to be clamped by the voltage of the supercapacitor plus a couple of diode volt drops in the bridge rectifier. So we should get about 7 volts or something like that, and probably if we measured the DC we'd probably get that. This is looking actually at the before bridge rectifier voltage, but I was just interested in the wave shape, which this actually shows reasonably well. Let's move to a different capacitor. Let's move to this one, and the frequency, which is just about 3 kilohertz. I can hear it. I expect you can as well, and you can certainly see it on the little scope meter. So still waiting for the capacitor bank to come up to voltage. Now at some point when the voltage on this cap gets into about the 7 volt range, this thing, which is currently at 7.23 volts, will switch from constant current to constant voltage, because as I say, I've set this to 7.55 volts constant voltage. So then the current will start to fall away and this will climb a little bit more slowly, and that will actually be quite useful when I start to attempt to use this transformer, this inverter, to balance this supercapacitor block. The first capacitor that lights up, the one that reaches its maximum 2.5 volts first, I'm going to draw energy out of it into the inverter and transfer that energy, some of it, not all of it, because actually these components get quite warm, so some of it is lost in heat, but I'm going to transfer the rest to the entire block of supercapacitors. So I'm going to draw energy out of one capacitor and put it into all of them, and that should enable me to balance the cells. So we're getting close to 7.5 volts now. The current is falling away because this has gone into constant voltage, so this has got 7.55 volts across the output, slightly higher than the voltage across here, of course, because there's a drop in these cables, particularly the red one because it's a noddy little cable. So we're down to 500 milliamps, and oh yes, I can just see that capacitor 1 there is starting to light its LED, but not the other two, so I need to balance that. Let's put this across the first capacitor. On comes the oscillator. You can see that on the scope there. Take that off, and yeah, all the lights have gone out, so I've balanced the pack. Which one's going to come on next? Well, that one is coming on again, so I'll do a little bit more balancing. Yeah. Can you hear the 3 kilohertz? I can hear it quite loudly. Now, of course, I'm transferring energy from the left-hand supercapacitor into all 3, and now you can see that the right-hand one is coming on. So now I need to move my balancing system over to the right-hand one, start drawing energy out of that, putting into all 3. Oh, now the middle one's coming on. Of course, they're reasonably well balanced because I was doing all this yesterday, so they're not out of balance really at all. So let's just pull some energy out of the middle one into the inverter oscillator, inverter, convert to AC, and then rectify back to DC again. So now we've got the first, we're down to 400 milliamps. The first capacitor is now got ahead of the other 2. Let's pull some energy out of that and put it into all 3. Of course, the energy comes out of capacitor 1 and also goes back into capacitor 1. There are losses, of course. There are losses in this. These transistors are probably getting quite warm now. Yeah, they are. Yeah, they're moderately warm. Okay, we need to balance capacitor 3. That one seems to have got ahead of the pack. Capacitor 2 is now in the lead. Oh, 1 and 3 are now coming on almost together. So I think that's it. I think that's pretty much balanced. When capacitor 2, the light comes back on, and it has, they're all 3 on now. So that is a balanced pack, and we're nearly at 7.5 volts. So what's the point of all this? Well, the idea is to have one of these little mini inverters, and hopefully these could be made even smaller, have one of them on each capacitor. On the protection boards, you'd have one of those voltage detectors and a MOSFET, and that would turn this thing on. And rather than just dumping energy into a resistor, which is wasteful, you take the energy and you transfer it to the entire pack. Now, I can't see any reason why I can't have 3 of these with their bridge rectifiers all connected in parallel to the pack, because they're all going to act as anti-backfeed diodes, so nothing can get from the entire pack back through the inverter. So they should sit happily side by side. So if I had 3 of these things all connected up to individual capacitors and little push buttons, I could press these push buttons and just balance this pack dynamically as it was charging. It's perfectly in balance now. Absolutely spot on. This is just about to come up to 7.5 volts. We're down to 240 milliamps. These protection circuits are on, so that's where most of this current is going. These boards have little I don't think they're MOSFETs. I think they're bipolar transistors and groups of resistors. You might be able to see, yeah, it's hard to see, but there are little triple groups of resistors on the bottom of each of those boards. So they're balancing anyway, but I can do additional balancing with my little inverter. So let's take the middle one and totally unbalance it by drawing some energy out of it, passing it to the entire pack, and then they're out of balance. It'll come back into balance, of course. No worries. That light will come back on soon. And they'll all balance up. There it goes. And we're nearly at 7.5 volts. So that was the purpose of this, to see if I could do active cell balancing rather than just dumping into resistors, by having the energy transferred out of a cell and into the entire pack. That, of course, requires that the DC is converted to AC, which is what the Royer oscillator does. The transformer is for galvanic isolation, so that this can be placed at any part in the series string, at any potential in the series string. Bridge rectifier, which this module also includes, which is why it's so convenient, to turn it back to DC. We've now got a higher voltage DC. And then, of course, that is clamped by the voltage of the supercapacitor pack, which is why you get those flat-topped sine waves. Now, just one other thing. I'm quite interested in how much current is being drawn out by this inverter module. These balancing circuits, I think, are capable of about 0.5 amp. So I'll just put my ammeter here in line with this. So let's draw some current out. And it's 0.88 amps, so about 880 milliamps, about 90 possibly. 900 milliamps, sorry, so 0.9 of an amp. So certainly this transformer module is drawing a heavier balancing current than the built-in protection circuits on these supercapacitor protection boards. So it'd be nice if we could get this current up a little bit, but getting close to an amp being pulled by this thing, a little bit being burnt up in heat in the transistors here, but a fair proportion of it being transferred back to the pack. So it's an energy efficient balancing system rather than just dumping it into resistors and wasting it. This is recycling it. It's green. It's eco. So there we are. Cell balancing by using an inverter-based cell to pack energy redistribution. It's green. It's environmentally friendly. And it's pretty wacky, really. Cheerio. So if we switch this thing to Hertz, we can see that it's running actually at quite a high frequency. What is up with this?